Hi everyone, this is Daniele Gamelli, and on behalf of my collaborators Kaidi Yang, James Harrison, Philippe Rodriguez, Francisco Pereira, and Marco Pavone, I'll be presenting our work on graph neural network reinforcement learning for autonomous mobility on demand systems. At its core, autonomous mobility on demand aims at bringing together recent advances in autonomous driving technologies with the emerging concept of mobility on demand, whereby customers typically request a one-way ride from their origin to a destination and are served by a shared vehicle belonging to a larger fleet. In a context where private cars are widely recognized as unsustainable for personal urban mobility, AMoD systems have the potential to enhance the benefits of traditional car sharing and mobility on demand systems by allowing for an automated and centralized control. However, controlling AMoD systems potentially entails the routing of thousands of robotic vehicles within complex transportation networks, which makes the AMoD control problem an open challenge. At a high level, existing literature on real-time coordination of AMoD systems can be classified into three categories. The first class of methods applies rule-based heuristics that, although efficient and relatively simple to implement, can rarely yield close to optimal solutions. The second category designs model predictive control approaches based on network flow models. Given an accurate analytical description of the system, these methods guarantee close to optimal performance. However, the resulting optimization problems are typically formulated into large-scale linear or integer linear programming problems, which may not scale well for complex AMoD networks. The third and most relevant category for this work employs learning-based approaches to devise efficient algorithms able to handle stochastics and unknown environments. However, learning-based controllers are faced with the challenging task of assuring reliable system performance when deployed in scenarios outside the training distribution, and where, to the best of our knowledge, their generalization and extrapolation properties are essentially understudied. Therefore, the question we ask ourselves is the following. In order to address some of the challenges of learning-based approaches, which properties of the AMoD problem can we encode in the design of neural network architectures? And what is their impact? At the heart of our work is the idea that the AMoD control problem is fundamentally characterized by graph-based computations. And because of this, we argue that exploiting the graph structure can represent a new direction for addressing relevant challenges, such as transferring learning beyond the training conditions and learning from small amount of experience. To be more concrete, in the context of urban mobility, transportation networks are naturally defined through graph representations, whereby, for example, node represents areas in the city and edges the connectivity between them, such as in the figure on the right. In this work, in order to exploit the underlying graph structure, we propose the use of permutation invariant computations, such as graph neural networks, to centrally control AMoD systems. We argue that graph neural networks exhibit a number of desirable properties and propose an actor-critic formulation as a general approach to learn proactive, scalable, and transferable rebalancing policies. At a high level, the AMoD control problem can be split in two main objectives. First, vehicle dispatching, or concretely, the assignment of idle vehicles to customers requesting for transportation. Second, vehicle rebalancing. That is, for vehicles not matched with any passengers, the operator will either have them stay at the same station or rebalance them to other stations, such as, for example, to anticipate future demand. In this work, we embed the proposed deep-RL module within a three-step framework. In the first step, we solve a matching problem to assign available vehicles to passengers with the objective of maximizing total profit at a single decision step. The second step entails determining the desired distribution of idle vehicles by using a learned behavior policy pi. Specifically, given a current state of the system ST obtained after dispatching, the learned behavioral policy will have the task of describing a categorical distribution over stations, indicating the percentage of idle vehicles to be rebalanced in each station, as shown in the highlighted figure on top. By doing so, we define a problem where we have an action at each node as opposed to along each edge, which significantly improves scalability of training and implementation. Lastly, in the third step, we convert the desired distribution computed in step 2 into actionable rebalancing flows by solving a minimal rebalancing cost problem. In this context, our work focuses on devising deep RL agents for step 2 of our three-step framework. We formulate the rebalancing problem as a Markov decision process, where at any given time t, the state st encodes contextual information characterizing the state of the transportation system. The goal of our agent will then be to output a distribution over nodes in the graph or areas in the city, representing a desired displacement of vehicles in our system. Formally, we represent this by parameterizing concentration parameters of a Dirichlet distribution. We train this rebalancing policy under the objective of maximizing service provider profit. At a high level, we propose an advantage actor critic formulation where both the policy and the value function estimator are characterized by graph convolution layers and are jointly optimized to maximize expected profit. The main intuition behind the choice of this architecture is that throughout graph convolution, our agent will take the form of a shared, node-wise controller with the ability to aggregate information from neighboring areas. Each node will then locally contribute to the computation of the Dirichlet concentration parameters. The critic, on the other hand, is then characterized by a symmetrical architecture with the exception of a global pooling layer, which enables for a computation of a single value function estimate for the entire network by aggregating information across all nodes in the graph. A fundamental property which we believe to be essential for learning effective control policies in transportation engineering broadly, and AMoD in particular, is the one of permutation invariance. For illustration, consider a graph representation of the transportation network comprised of n nodes, whose attributes are denoted by the colored vectors on the slide. Now, let's assume we want to devise a control policy through standard neural networks, such as multi-layer perceptrons. To do so, we are forced to unroll all features in the graph into a big state vector. By doing so, however, we are unwillingly committing to a specific ordering of the nodes in the graph. In other words, if we just conceptually reorder nodes in the graph, a non-permutation invariant computation, such as in the one in multi-layer perception, would consider each ordering as fundamentally different, and thus require an exponential number of input-output training examples before being able to generalize. On the other hand, control problems on graph structured data requires functions that are invariant to permutations, which we claim has the potential to improve the performance and generalization of learning-based AMoD control policies. In our experiments, we use real-world trip travel data to generate realistic urban mobility scenarios, where our agent will be orchestrating a fleet of autonomous vehicles to satisfy demand for transportation of different users. Empirically, our goal is to answer the following questions. First, can we learn our rebalancing policies in real-world scenarios through reinforcement learning? And if we're able to do so, how transferable are the learned policies across different scenarios? And lastly, from a computational perspective, how do we compare against control-based approaches? Throughout our experiment, we mainly monitor three key performance indicators: average reward or profit, number of service customers as a proxy of demand satisfaction, and the overall cost of rebalancing, that is, the cost incurred by the model for balancing trips only. When looking at reward, we also compute the percentage deviation from MPC, as this model represents an optimal upper bound of performance, aware of the exact future evolution of the system. Apart from control-based approaches, we also benchmark against heuristic-based and tabular RL methods, as well as an ablation of our actor critic formulation. In practice, we benchmark our methods on real-world datasets from the cities of New York and Chengdu, where we first train and deploy on different instances within the same city. The tables on the slide show that A2C GNN, our model, can learn the balancing policies able to achieve close to optimal system performance on both tasks. Specifically, our model's performance is only 2.2% and 1.6% away from the Oracle performance in New York and Chengdu respectively. In all further experiments, we focus on extensively benchmarking the transferability and generalization capabilities of our approach. Here, for example, we study the extent to which policies can be trained on one city and later deployed to the other in a zero-shot fashion, in other words, without further fine-tuning. Specifically, in this simulation experiment, we select the pre-trained policy on Chengdu data and examine its zero-shot performance when deployed in New York's transportation network, and vice versa. In particular, despite the substantially diverse mobility patterns, the zero-shot policy shows only a slight drop in performance when compared to its fully retrained counterpart, 1.4% for New York and 2.5% for Chengdu. From an application perspective, policies with structural transfer capabilities could enable AMoD operators to expand their service to new cities without having to train new control agents, thus being able to reuse actionable knowledge from other service locations. We also study how well A2C GNN can generalize to the case of a hypothetical service area expansion, and show how, Despite a 300% increase in service area, as in our example, our zero-shot model is only 2.5% less profitable when compared to its fully retrained counterpart. Notice how this experiment represents a set of common real-world scenarios. For example, consider a service provider interested in expanding its service area without having to retrain a control policy from scratch. Or alternatively, in case of extremely large Uber networks, one might consider training a policy on a specific subgraph of the network and later being able to deploy the learned policy on the entire system. Our experiments also show how well the pre-trained A2C GNN can be applied to arbitrary, non-grid-like transportation networks. Crucially, the setting highlights how the permutation of areas and the reduced joint positioning would make agents based on multi-layer perceptions and convolutional neural networks ill-defined, as these are simply unapplicable for the task. Lastly, we studied the computational cost of A2C GNN compared to MPC-based solutions. As shown in the plot, we compare the time necessary for both approaches to compute a single rebalancing decision. We do so across varying dimensions of the underlying transportation network, ranging from 16 up to 400 stations. The results show that, once trained, learning-based approaches allow for fast computation of rebalancing policies by forward propagation of the current system state through the learned policy. From a theoretical perspective, our approach exhibits computational complexity linear in the number of nodes and graph connectivity, as opposed to control-based approaches which scale superlinearly in the number of edges. To summarize, we propose the use of graph neural networks to parameterize reinforcement learning agents for AMoD systems, as we claim these are able to encode fundamental properties of the AMoD control problem. We benchmark our method against both learning-based and control-based approaches on real-world datasets. We find that our method is able to achieve close to optimal performance in terms of operator profit and customer satisfaction, with significant computational gains when compared to state-of-the-art control-based approaches. We focus on assessing transfer and generalization capabilities of deep RL agents. Specifically, we find agents based on graph neural networks exhibit interesting zero-shot transfer performance on tasks like intercity portability, service area expansion, and irregular geographies. We believe this work opens a number of interesting research questions, like the use of meta-RL for fast domain adaptation, offline reinforcement learning to leverage vast offline datasets of urban mobility, or the integration of the learned control algorithms with co-design frameworks for the design of services, for example, fleet sizes, vehicle types, and so forth. There are a number of methodological and empirical aspects of this project I didn't get the chance to talk about. Please read our paper or reach out to learn more. Thank you for your attention.